Yep.
And okay, great. Hear me? Yep. Um, thanks, David. Thanks again, Jan. So thank you all for attending. I'm going to be talking about a project I'm working on with David Walpert. So this project, it's the preprint is almost ready. It's not up yet. If you're interested in the things I'm going to talk about, please feel free to email me and maybe I can send you a draft. Okay, so there's two main goals to this project. The first goal is to derive bounds on entropy production and on extractable work, which are involved in transforming some initial distribution P to some final distribution P prime. That's the basic setup we think about. And these bounds arise from constraints on the kind of driving protocols that one can apply to the system. And this is primarily what I'll be talking about today, and I'll show you that we can use some ideas from information geometry and some other ideas to derive some interesting results here. And the other goal of the project, which I'll mention mainly in passing at the end due to time reasons, is to use these bounds to think about the thermodynamics of information in the presence of constraints and how different measurements can have different thermodynamic values, so to speak. Okay, as I mentioned, I'll mainly talk about the first goal, and I will explain this using a simple example of a Szilard box, which many of you are familiar with. So a Szilard box that I'm going to consider, there's a single particle in a box, and there's a vertical barrier that we can move left and right. And let's say that we find out that the particle is initially in the right half of the box with probability 1. So this is the initial distribution. And we actually want to, let's say, extract work this from this initial distribution. So this is kind of the common setup that's part of Maxwell's demon as often formulated, and so on. So we can apply a driving protocol to this system by moving the barrier left and right. And in particular, we might, for example, move the barrier to the middle of the box and then very slowly expand it leftward while, let's say, raising a weight or a pulley or something like that. Now, how much work can we extract during such a process? By the second law of thermodynamics, at least one formulation of it, we know that the maximum amount of work we can extract is upper bounded by the drop in what's called the non-equilibrium free energy. And the non-equilibrium free energy is the expectation of the energy minus kT times the entropy of the distribution. Okay. And the excess of this inequality, so the difference between the maximum amount of work we can extract and the actual amount of work we extract, is called, or is proportional to what's called entropy production, which measures the intrinsic wastefulness or dissipation involved in the process. Okay, let's think about this particular minimal example, the box. Let's say we start and end with a uniform energy function. So the equilibrium distribution is just uniform throughout the box. Then a simple calculation shows that the maximum work we can extract, so the drop in the non-equilibrium free energy, is given by kT log 2. T is the temperature of a heat bath that's coupled to the box. And if we actually do the protocol I outlined here, where we rapidly move the barrier to the middle and then expand outward, we actually can extract all, or at least, almost all of that work up to kT log 2. And we can extract an arbitrarily, we can dissipate an arbitrarily small amount of entropy production in such a process. Great. Okay, well, now let's consider a slight variant of the previous setup, where we still have the Szilard box, a single particle, a vertical barrier, but now we initially find out that the particle is located in the top half of the box with probability 1. So let's say we still want to extract work from this box by bringing it to its uniform equilibrium distribution somehow, right? And we want to ask, okay, well, how much work can we extract from this initial distribution? Now, at least, if we do the calculation of the drop in non-equilibrium free energy, it's exactly the same. It's kT log 2. So what the second law says in this example is the most you can possibly extract is KT log 2. But intuitively, it seems that there's no way that we should really be able to extract any or at least much work from this box by using a vertical barrier, right? It's just not clear how you would do that. So we could extract zero work by just letting the particle equilibrate to the uniform energy function, but that would extract zero work and that would dissipate log 2 of entropy. Maybe we could do something else, not sure if we could ever extract work. So the general kind of motivating question is, first of all, can we actually prove that work extraction is impossible in this case, and maybe some kind of more general set of cases that includes this one? And more generally, can we kind of formally derive some kind of bound on the amount of work we can extract, which is stated in terms of the drop of some kind of effective free energy? So not the full non-equilibrium free energy that I talked about in the previous slide, but some kind of smaller quantity that says, given the constraints that we're faced with, this is how well you can do. Now, by constraints, I've mentioned this word many times. What I really mean is things like what kind of energy function and what kind of stochastic dynamics we can apply to the system of interest. So in this case, the constraint would be that we just have basically our degree of freedom of control is just moving this one vertical barrier. So we think this is quite relevant because, of course, in the real world, most of the time we're highly constrained in how we can manipulate a system. And that should give some interesting bounds that are tighter than the second law on how much entropy production we have to cause and how much work we can extract. By the way, yes. So that was the kind of motivating example. And I'm going to now describe our general approach, starting with the physical setup that we consider. So we think of a physical system coupled to one or more thermodynamic reservoirs. So the formalism of stochastic thermodynamics applies. The system undergoes what we call a driving protocol. So this is a time inhomogeneous trajectory of dynamical operators, which we label by L of t. So these can be rate matrices, or for discrete state systems, these can be Fokker-Planck operators for continuous state systems. And the distribution of the system evolves according to this L of t at time t. And they can change over time. And when we apply this driving protocol to an initial distribution p, so at time 0, it brings it to a final distribution at time tau, which we label by p prime. And we can kind of use this visual language to show what we're doing. We start with p, we end at p prime, and the tangent at each point is given by this dynamical operator. Okay, so given a driving protocol initial distribution, we know how to define and calculate entropy production, which I write as sigma, using tools of stochastic thermodynamics. And we can also calculate the work as the difference between the drop in the non-equilibrium free energy minus the dissipated work, which in this case is KT times sigma. So now we introduce the notion of constraints on the driving protocol, and we do this in a fairly general way in the following manner. We say the driving protocol is constrained, and by that we just mean that at all times t, this dynamical operator L of t belongs to some set lambda. And lambda is just some restricted set of dynamical operators. So for example, for the Szilard box I talked about above, previously, the elements of lambda, the dynamical operators, would be different Fokker-Planck operators corresponding to locating the vertical barrier at different horizontal locations. So the horizontal location would specify a particular energy function, and then we would have a diffusion term in addition to that, and that would be one particular element of lambda. For a discrete state system, lambda would be just the set of rate matrices that we are allowed to use, whatever those are. Okay, notice we don't think of constraints here in some other ways that people have thought of constraints, such as things like finite time. And I'll now talk about some of our results, which is given this formulation, can we derive some pretty general formulation, very general at this point, can we derive some bounds? So to introduce our results, I have to talk a bit about some preliminaries from information geometry. And I will say both of these concepts are defined relative to some set of distributions omega, which at this point I'm going to leave unspecified. Okay. So the first preliminary is the notion of an information projection, which some of you are familiar with. It's a very standard tool from information geometry. And the information projection of some distribution P, which I write as pi omega, to the set of distributions omega, is just the closest element in omega that is closest to P under the Kolchinsky distance. Okay. And the second idea I have to introduce, so information projection is very standard, many of you have seen it before, is what I call the commutativity of the dynamics and the projection. This is not a standard idea, so this is something that we introduce. And we say that this set of dynamical operators, lambda, commutes with the projection to a set of probability distributions, omega, if basically for all the elements of L in lambda, the operators e to the L and the projection to omega commute with each other. Okay, this is just math, and let me just show you what it means and visually. So it means that, let's imagine our system is evolving over time, and at time t, it has distribution pt. So this is its dynamical evolution, let's say, according to dynamical operator L. So we can either push it forward under e to the L, and that would be the pushed forward distribution, and then we can project the pushed forward distribution to omega, or we can first project the distribution to omega and then push it forward under the dynamics, and they commute just if basically we end up at the same exact point under both of those possibilities. So either way we go. So this is basically a condition between, again, a set of dynamical operators lambda and a set of distributions omega that we will make use of in the following results. So, okay, now what is the result? Again, I'm going to present a kind of mathematical result first, which we use in a couple of different ways. If it seems awfully abstract, just wait until the next slide when I talk about kind of a much more concrete application of it. But there is a more general result. And we can think of this general result as essentially connecting, on one hand, things like stochastic dynamics, on the other hand, things like information projections. So let's say that we have some driving protocol that transforms our system of interest from initial distribution P to final distribution P prime. And we make the following assumption, or we place the following restriction, that the dynamical operators, all we know is that they stay within lambda for all t. So this is a constrained driving protocol, constrained by the set of dynamical operators lambda. And we know that lambda commutes with the projection to some set of distributions omega in the sense that I just described in the last figure. Then we can derive the following bound that says that the basically decrease in distance over the course of the protocol from the state of the distribution of the system to its projection, first of all, is non-negative, and second of all, is a lower bound on entropy production. So again, let me visualize this. Let's say we have the initial distribution P, and it can be projected to omega. We have the dynamics of the system transform into a final distribution P prime. We can again project it down. So the decrease in the distance to this manifold omega, first of all, we show it must be non-negative, and it is a lower bound on EP. So we basically, however much closer we get, and we have to get at least a little bit closer, or we can't get further away, that has to be dissipated. It turns out that this also, under a mild condition in omega, this lets us decompose the non-equilibrium free energy, which I write as this curly F here, into two terms. So the first is the effective free energy, and the second one is what we call the inaccessible free energy. So the effective free energy in P is actually just the projection, is the effective free energy of a different distribution, which is P projected to omega. And we can see by the relationship between entropy production and work that actually this drop in the effective free energy is what bounds the work we can extract from the system. So essentially, so another way of saying it is we can only extract work from sort of the closest distribution in omega to P. And this Kullback-Leibler divergence, which is the inaccessible free energy, must be dissipated away, as seen in the result in the pink box. Okay, again, this is pretty abstract. Let's talk about a concrete application. So we've applied it actually in a couple of ways, but this is maybe the primary way. So the first thing we think about is symmetry constraints. What do I mean by that? Well, let's say that the dynamical operators obey the symmetries of some group G. And by that, we just mean that all the dynamical operators in lambda commute with some transformation with the transformations in the group G. In that case, we can show that the set of dynamical operators lambda commutes with the projection to omega, which is the set of distributions that are invariant under G that essentially have the same symmetries, the symmetries encoded in G. So, and we have the bounds I talked about before, where pi omega is just basically a projection that projects a distribution P to the closest distribution that has the symmetries of G to P. So let me demonstrate this with the Szilard box. So we have the Szilard box, and the key idea here is that no matter where the vertical barrier is located, it has this vertical reflection symmetry. The Fokker-Planck operator is invariant if we just flip the y coordinate, and it's not invariant if we flip the x coordinate, right? Because that would change the location of the barrier. So it's only invariant under the y coordinate. In this case, we can say that omega is the set of distributions with vertical reflection symmetry that basically is invariant under that same symmetry. And here's just some examples. These are vertically, right? All kinds of distributions. There's of course an infinite number of them in omega, but these are some of them. They're all symmetric above under reflection of vertical reflection. Okay, so now we can think about projecting different distributions to this set. So if we, for example, project the distribution where the particle is on the right half of the box, then it actually projects to itself because it's already symmetric. If we take the distribution where the particle is in the top half of the box, it turns out that the closest symmetric distribution to that is the uniform distribution. We can now plug these projections into our work bound that's stated in terms of effective free energies. And we get this, if we basically ask how much work can we extract given these constraints and bringing these initial distributions to a final equilibrium uniform distribution, then we get these bounds. So it says that the left distribution, we can actually extract up to KT log 2, and the right distribution, basically the effective free energy is the same at the beginning and end. We can't extract any work. So this proves rigorously that there's no way, I mean, in this simple case, that there's no way to extract any work from the distribution on the right using a vertical barrier. And of course, this generalizes to all kinds of other symmetries in other setups, so not just this one. Okay, so I'm just gonna kind of rephrase a few of the takeaways here beyond the example. So first of all, the distance between P and its projection, we can think of the measure of asymmetry in the distribution P relative to group G. So it vanishes if P is invariant under that group. And the above result says two things. First of all, it says that asymmetry measured in this way can only decrease under basically symmetric driving protocol. And this is a kind of an irreversibility result, right? It says what kind of transformations are even possible at all. those in which asymmetry decreases. It also says any decrease of asymmetry has to be dissipated as entropy production. So a takeaway message here is that, if there's a simple one, that symmetric driving protocols could never extract non-equilibrium free energy that's in the asymmetric part of a probability distribution, so to speak. Okay, I am nearing the end of my talk. I'm just going to talk about this is my last slide. And I just want to briefly mention one interesting application of these ideas, something that me and David are very interested in, is using these results to think about the thermodynamic value of different kinds of measurements. So many are familiar with this equation, which is sometimes called the second law with, inequality, second law with information, which basically says that if we make a measurement of a system and we acquire some number of bits of information about the system, here, this is the mutual information term, IXM, then afterwards, we can use that information to actually increase the amount of work we extract from the system by KT times the number of bits. Well, the funny thing about this is this result, which is of course an inequality and very general, it's not sensitive to which kinds of measurements we make. But in general, we expect that if you want to extract work from a system, your measurements should in some sense align with the ways in which you can manipulate the system, right? And so for example, if I ask which one bit measurement is more valuable to somebody who can move around a vertical position, measuring left or right, or measuring top or down, which half of the box the particle is in. So the bound that's shown at the top of the slide says, okay, well, in principle, both of these can increase the amount of work you can extract by KT log 2. But we can use the kinds of results I just talked about to show that the effective increase in work due to the measurement on the left is KT log 2, while the effective increase in work under the measurement at the right is actually 0. So that's a completely sort of useless measurement. You would pay for it thermodynamically, as we know, but you can't use it to extract work. And so more generally, we can use our approach to think about the information acquired in a measurement and decompose it into the valuable information, the worthless information, where valuable and worthless are defined again relative to how can one manipulate the system. Okay, so thank you very much, and I think we can go to questions if there's any.